Welcome, everyone. Does this mic sound good out there? Okay, great. Thank you for joining us for the 2026 F.A. Gilfillan Memorial Lecture. I'm Eleanor Feingold. I'm the Dean of the College of Science here at Oregon State University. Tonight, we have the privilege of honoring David Gee, a globally recognized leader in energy research. I want to start, however, with a land acknowledgement and recognize that Oregon State University has had an impact via its land grant history on the indigenous communities in Oregon. Oregon State University in Corvallis is located within the traditional homelands of the Marys River Band of the Kalapuya, who were forcibly removed to reservations in Western Oregon. Today, living descendants of these people are part of the Confederated Tribes of the Grand Ronde Community of Oregon and the Confederated Tribes of the Siletz Indians, some of whom are part of the Oregon State community today. We deeply value their presence and ongoing contributions to the university and to the College of Science. We also take ownership of the need to mitigate the continuing impact of the land grant history on these communities. The Gilfillan Lecture, a long-standing tradition in our college, brings us together every year to celebrate outstanding science at OSU in honor of Doc Gilfillan, whose record of extraordinary science has positively impacted generations here. Francois, Doc Gilfillan, served as Dean of the College of Science for nearly 25 years, a record I will not be approaching, from 1938 to 1962, and also served as acting OSU president from 1941 to 1942. The Gilfillan Memorial Award honors Doc Gilfillan's life and recognizes his extensive service and contributions to OSU and to the field of pharmaceutical chemistry. We're very grateful to the Gilfillan family for establishing this award and lecture and for helping us keep Doc Gilfillan's legacy alive in so many ways on an ongoing basis, most recently with the Nancy Gilfillan Jensen Graduate Scholarship. The first recipient of that scholarship was named this year, Angela Zullo, who's pursuing her PhD in biology. Angelina was not able to be here tonight, but we wanted to recognize that award. So now for the main event. It's my honor to introduce Julie David Lee, the 2025 recipient of the F.A. Gilfillan Award for Distinguished Scholarship. From challenging long-held beliefs about which ions move in batteries to developing entirely new battery chemistries, Gee has built a career proving that innovation often comes from asking, why not? David has built an extraordinary body of work by asking bold questions that others overlooked. His research has challenged assumptions in energy storage and led to new battery chemistries that are safer, more sustainable, and potentially transformative for grid storage and electric transportation. His lecture tonight, A Chemist's Journey, Unlocking New Battery Chemistries for a Sustainable Future, showcases moments when confronting the status quo led to breakthroughs that could help solve some of the most urgent energy challenges of our time. David holds the Bert and Emmeline Christensen Professorship of Chemistry and is a highly cited researcher with more than 48,000 citations and an H-index of 99, for anyone who knows or cares what that is, reflecting the broad influence of his work around the world. His research has appeared in top journals, and he's secured major funding from the National Science Foundation and the U.S. Department of Energy, including multi-million-dollar awards to develop safer, high-performance battery chemistries. We're thrilled to celebrate David's achievements tonight and look forward to his presentation. Let's welcome him to the stage.
Thank you, Eleanor. Thank you, Eleanor. All right, let me get a timer started. Hello, Beavers. How are you? Great. I feel humbled. It's my great honor to receive this award, and my great honor and pleasure having you here. So let's get started. All right, so we are all about sustainability. It is a concept we reinforce in the lab almost daily, right? So I'm going to talk to you about the journey on this concept. First of all, I want to thank the Gilfillan family for their support to OSU, to the college. It's a great honor, right? And we are here every year to celebrate the legacy of Dr. Phelan for his scholarship, mentorship, and service. And I resonate the most his service mindset, right? Public service with education. And if you've been to OMSI, Oregon Museum of Science and Industry, you have been benefited, right? So it's a great honor to receive this award. So let me start using this song. Okay, it's moving. Moving too much? You know, sometimes, no matter how well you prepare, you know, things will happen. So a little bit about me. Okay, so that's where I came from. See that red dot? A tiny town. It's called a Jingyu County. Okay, with a population in Chinese standards very small, 60K people, right? Size of Corvallis, one high school. And in my high school, I didn't have the luxury to play with tubes, beakers. I didn't have any experience of working on chemistry. So I blindly chose chemistry because of my love to the topic and also to my high school teacher, right? So, all right, so the area is stunningly beautiful, right? If you get a chance to visit there, it is worth the trip, all right? So, I'll probably just use this. I want to thank my parents. So they are teachers, so you see why I'm a teacher now. And they have devoted everything they have to my education and to the well-being of me. I can stand here today because of them. Right? So, and that was in 1986 in a Great War. Right? So, and as a family not that rich, we spend a lot of money actually for the trip, obviously. Right? So my dad is a physics teacher for my 8th grade and 9th grade. So I'm not exaggerating. I think he was my best teacher. His logic is clear. He's very vocal, and he's very funny. I'm not that good, right? So I'm trying. I'm performing. Right. So he's a talented cyclist and skater, right? He's no longer with us now, unfortunately. So my mom is here, who's trying to shoot the video. Right? So my mom is also have the last name of Kong. Where's Dr. Kong? Right? So yeah. So they're actually they're of the same generation. The Ling generation, right? After Confucius, that's the Confucius family. So my mom always supported me. Basically, she believes I can achieve anything if I tell her I'm going to do that. I'm going to try. So that's mom, right? 谢谢你妈妈. Yeah, thank you, mom. Thank you. So fast forward. 1999, I was accepted by Jilin University. University-wise, not very famous, but the chemistry program is one of the best in China. Still top 5. So I was working hard, and I got accepted in a lab doing undergrad research in a junior year. So I got the experience of working on some nanocrystals for 1.5 years. It was good. And so I have a really strong mentor, Dr. Hao Zhang. And he has a record. He had an idea, and he planned a research. He did experiment. He finished the draft. The next week, submitted. I was amazed, right? But still a high quality study in Chinese. It's easier for Chinese people to write Chinese papers. That's why it's fast, right? So that's actually polymer with nanocrystals that is fluorescent. So I got into this materials field early on, okay? And we got a paper in Advanced Materials 2003, right? That's kind of 20-some years ago. And then moving forward, I got an offer from Waterloo, University of Waterloo. Back then it was hard to get a visa to the US. So I went to Canada instead, and working with Professor Linda Nazar. She's really good. Actually, she does one thing that I still try to emulate. If she's editing her students' papers, she's going to actually force you to sit there doing nothing, watching her editing the paper. Right? So basically, you're going to read the thought process. You're going to actually, find how she changes things. Flip the paragraphs, tweaking the little things of journal figures. And if I force you to do that for my group students, you know where that came from, right? Yeah. So, and then I obviously spent a lot of time in the lab, right? And I love spending time in the lab because the conditions are better than my bedroom. In summer it's easier, right? In winter is warmer, right? So, and also with Tim Hortons, who is drinking Tim Hortons? We have some Canadians, right? Addison, right? It's really helpful, right? Double is really good. It gives you a lot of energy. So with that, we have a paper published. This is still my most cited paper, almost 6,000 times citations. And then I want to show you we are not just boring, dull researchers, right? We had fun. This is actually a Lunar New Year gala we had of University of Waterloo. I was a performer. Right? I was like a singer, right? So even from my college time, I probably went on stage like a few times, and I did that for my PhD. You can hear for 15 seconds. It's in Chinese. It could be loud, right? So bear with me. Wow. I hope that's not too bad. That was exactly 20 years ago, 2006. So, all right, so let's see. Oh, don't play that again. Then I met my wife. Angela is here. So I'm a lucky man, right? What you can say. So she's extremely supportive in my career, and she convinced me that, he told me, David, you probably can be a faculty member someday. I was like, really? I want to be in industry. I worked on batteries. I want to actually invent batteries for vehicles, for electric vehicles. But she said, you probably can be a professor. I listened to her. Here I am. So listen to your partner, right? Then we got an offer, for my postdoc. We went to UCSB. So we tried something that is crazy. We drove across the continent in December. It's about December 10 to 20. We saw cars flipped, literally. Yeah, so it was dramatic. But that is when I started loving this country. It is truly beautiful, right? If you have done that, you will agree with me. So now we are at UCSB. I worked with Professor Gillian Stuckey. I also got a mentorship, I think, from Professor Moskowitz. I still remember a very well-known, his meshes, right? His a very important lesson to students and maybe faculty members. He told us, one paper, one meshes. Just sharpen that meshes, right? Then your paper will be strong. So, and then, fast forward a year and a half later, I got an offer from OSU. I'm about to become a beaver. And then ARPA-E is agency similar to DARPA. but it's DOE, right, agency. Got a call for funding. And so Professor Stuckey forwarded the forward to me, and he said, David, do you have an idea we can write a proposal? Well, I said, okay, well, I thought about that carefully, and I went back. I said, I have a deal for you, all right? So I have a plan, because I have an idea for OSU. But if I write it here, could you make me a co-PI? And he said, yes. And we wrote a proposal, we got funded, right? That's how I got the first funding from OSU. So Professor David Austin also helped editing the proposal. So very important experience, very important. Now I'm a Beaver, right? So for the last 13 years, what do? We do hypothesis-driven research, right? To discover new properties of not just materials. If you consider, water is a material, well, that could be a material, but we probably want to make it broader, right? Matter, rather than just materials. So I have many people to thank, right? I want to show them here. These folks are amazing. So you couldn't believe, sometimes secretly, I feel how lucky I am. It's definitely a privilege to work with these folks. And they have their time dedicated to your vision. Think about it. They dedicate their time to your interest, right? And you overlap your life with them. 1 year, maybe 3 years, maybe 5 years. So it's a fantastic thing to have, to be a faculty member, right? I have undergrad students, right? We have trained about 65 undergrad students. Some of them are really doing great things out there. So it's an honor to train them as well, right? And some of them are here, right? Thank you for coming. So I want to thank our department heads. Mike is here, and Rach was before Mike and Wei. Without their help, things can be hard, right? They removed every single barrier you could possibly have to make sure you can be successful, right? What a fortune we have, right? And my collaborators, and many of them are here. So they are my best friends and allies on campus. Right? So we can get things done. And my external collaborators, you can get synchrotron done, you can get neutron done, high resolution, institute TEM, all kinds of fancy tools that we can access, right? So it's a virtual consortium you could build, right? That's fantastic. So now, let's move on to batteries. Okay. So what is a battery? A battery is a device that decouples electron transfer from the ion transfer, right? You got actually something burning. It's a redox reaction, right? That's actually mass transfer with ions and electron transfer with electrons, obviously, simultaneously, right? A battery device decouples that so that you can make sure electrons are moving in a clean pathway along wires. You capture that wire momentum with electrons, you have power, right? That's batteries. And batteries have electrodes, right? And have electrolyte. Inside the electrolyte, you have ions. And today, I hope I will use the ions as our guide through the journey, right? So, in a battery field, there are two grand challenges. What we can do with batteries? The first one is, actually we have a lot of smoky days, right? Smogs from the wildfire. So the globe is warming, and we're still burning fossil fuels. If you don't want to burn fossil fuels, well, natural gas probably is the best, but fossil fuels is still actually creating CO2. The alternative is renewables. You can have nuclear. It's difficult. Renewables is a lot easier accessible, right? So you need batteries to install the storage because renewables are intermittent. Sun do not shine all the time. Wind doesn't blow all the time, right? So that's challenge number one. Challenge number two, we want mobility, clean mobility, sustainable ways of moving around, right? And you know batteries can do that. So what is the metric to evaluate a storage battery? It has to be safe, right? You're going to build actually massive facilities, gigawatt facilities. You don't want anything wrong, anything bad to happen for that, right? Safety is the utmost criteria. The next is cost. We want the batteries to be as cheap as possible and sustainability, right? Because we're going to install them everywhere. That's the hope. Mobility, right? Cars, flying cars, right? And flying cars. Hopefully I can afford one in the future, right? So robotics. Who's going to dominate the market of robotics? With batteries that can last longer, having a longer driving range to do more powerful things, right? So that need the power batteries. And the power batteries, right now, we have been focusing on energy density alone. Sometimes fast chargeability, because we want a battery to be charged, 5 minutes, 10 minutes, at most half an hour, no more, right? We have not thought about sustainability yet, right? I will actually expand that later. Okay, so the EV age is here already. Look at what's the percentage of new car sales from January to August in which country? Norway. Almost 19% new cars are EVs. I mean, pure electric vehicles, right? So that is non-stoppable. It's coming. Now, another challenge. Who is going to dominate the AI age? Right? The people who know how to code? AI can code, right? Electricity. It's the electricity that is the limiting factor right now for the US. To get the data farms, right? Server farms, server centers to be powered. And right now, new gas turbines are fired up. There's a picture in Memphis, right? This cannot be the norm. We need renewable energy and we need to store them. All right, now let's get started with searching for new chemistries for storage batteries, okay? So I said ion charge carriers, the ions in the electrolyte is dictating the chemistries of batteries. It's defining the chemistry of the battery. So now, what are ions? What are materials we should use? They have to be sustainable. I love to use the term dirt cheap, right? I love that. I just feel so excited when something is dirt cheap. Especially for batteries. They're supposed to be dirt cheap. They should not come from the clean room. We should not use fancy equipment to make them, right? So rock-forming elements are the best, right? So next, economically viable, scalable, commodity, right? So industry already has it. Then it will be easier for us to use, right? So, and there's some elements that are not rock-forming elements like zinc, copper, but the production worldwide is massive, right? All right, so 2013, we started our journey, and we were landing on sodium. Sodium is, actually, you have taken some sodium today, right? Sodium chloride, right? Rock salt. So it's so abundant, right? It's abundant. I mean, I'm not talking about the sodium in the ocean, just the crust, upper crust, right? 3 orders of magnitude more abundant than lithium. So what we did, we found a mechanism in a field, and we didn't feel that is a correct mechanism. So we challenged that, and we published a new mechanism. And with that, we proposed a design principle for the material called hard carbon. Right? Hard carbon is the anode right now for sodium-ion batteries. Right? It's already finalized as the anode for sodium-ion batteries. So we were lucky enough, we entered the field when there were like probably 15, 20 papers for the entire sodium-ion battery field. Now look at it, it's $1 billion industry, right? So the paper we published was cited really well. Right? The field has accepted the mechanism we proposed. So now, we always flip the ideas. So we were working on sodium-ion batteries for 4 years, right? And that's actually about 3 years. Then we were thinking, why it has to be sodium? Philosophically, if it's not lithium, it has to be sodium? Who decided that, right? So then we asked that question, and we worked on everything else. Not everything, not exaggerating, but a lot of those stuff. So we become nomads of the periodic table. We travel a lot, right? From element to element. Our second stop, actually we have a lot of stops, but I want to show all of them. I'll just have some examples today, all right? So the second example is potassium. So potassium is also abundant. It's bigger. People don't like big things for batteries. They like small ions, right? Lithium, proton, that's better. Well, there is a prevalent assumption that you can store lithium ions by graphite. Graphite is still the anode material for lithium-ion batteries today, till today. You have that in your pocket. You also probably have some cobalt in your pocket, right? So graphite can be used to store lithium, and it's hard to store sodium in graphite. And somehow it was assumed graphite can never be intercalated by potassium ions. Even though potassium graphite intercalation compound exists. So then we got really puzzled. We searched the literature. We didn't find a paper talking about potassium ion battery with potassium ions intercalated. That is weird because thermodynamically, if that's available, you should be able to make it with batteries. So when we actually realized this, we were thrilled. We love low-hanging fruits. And that's right there, right? So we tested that. It worked. It worked, right? And that's how we got a paper in JACS. It was cited really well. And it was the foundation of the career award I received. All right. So sodium-ion batteries, potassium-ion batteries, they are called non-aqueous batteries. They use gasoline type of electrolyte, flammable electrolyte, okay? And in many ways, are they safer than lithium-ion batteries? Actually, I don't know. So see, that negates the original point that we want to have the batteries safe. So around 2016, suddenly we realized that, well, probably we should work on aqueous batteries. So we have a lot of water. I don't think you will disagree with me on that. Right. So the first ion we looked at is proton. Proton is the smallest, lightest ion, right? So why don't we use that? So now, as a fan of history, that's my second favorite subject in all over the schools, right? All the schools. So I dig the history up. I want to bring you back to 1806, and you go here, the nowadays Lithuania, right? This gentleman, his name is Theodore van Brosses. He left Lithuania back then to Rome. He spent some time in Rome. He wrote this masterpiece, Memoir on the decomposition of water and of the bodies that it holds in solution by means of galvanic electricity. The volta pile which is the real first battery, was invented about 10 years ago. And he was using Volta-Pell to study electrochemistry. And he proposed something really radical. And he said that the ion transport of protons can be done via this bond switching. Your covalent bond is switching to hydrogen bond is switching to covalent bond. You don't transfer the protons to transfer the charge of protons. You transfer the charges by not transferring the protons. Right? So it's fundamentally different from the common vehicular mechanism that you have the ions kidnapped moving across the solution. Right? So back then, actually, H2O was not known, but Grotius knows that water has hydrogen and oxygen. But the stoichiometry was not known. So, again, we dug in the literature. We didn't find a paper that literally enunciate their uses of Grotius mechanism to enable a really fast performance of proton battery. Again, we were thrilled, right? So, but how to transport protons fast? It does well in water. Then you install water in the electrode. You build highways of water in the electrode, right? And what's the definition of highways? Water talk to each other, but through hydrogen bonding. Hydrogen bonding network is what you need to be installed in the electrode structure so that it's going to conduct protons really well. And this is the computation. We have this material called Prussian blue. In specific, it's called a Turnbull's blue. Right? And 95% of all water molecules are in the network. Right? It's like they have Wi-Fi's. Right? They have Wi-Fi for them. And then you charge the battery. So the data here, 1C means you charge or discharge in 1 hour. 1000 C means you charge or discharge in 3.6 seconds. And the material delivers the same performance. 1 hour or 3.6 seconds. That's how fast this mechanism is. And with this fast mechanism, you can cycle the battery for a long cycle life. We got almost 0.7 million cycles. And we got a paper there. It's well cited. All right, moving on. We talked about that ions can move through water. Proton can move through water. And they can move in the electrode materials. The electrode materials, the particles of electrodes, it's probably 100, 200 nanometers. Well, by the way, nanometers 10 to the minus 9 meter, right? So, can we actually have protons moving across microns thick? Right? That's a scientific question. We want to have water alone as the electrolyte. So that means you don't need electrolyte, right? That means you got a dry battery, you put it into a humid room, you have a real functioning battery. You don't need electrolyte, right? So that's the product we probably will develop soon, but you can actually just use water. That's the question. So, yes, we can. This is the data, Yiming's data. We have pure water. We try to make sure CO2 is not dissolved in the cell. It works. This is charging. This is discharging, right? Very reversible. What is even more remarkable? We tested ice. The paper is under review now in Nature Materials, hopefully. I don't have a spoiler for the paper. We have ice. You got protons transported from one side of a piece of ice through that by the hydrogen bonding, covalent bonding of water molecules, right? And those water molecules are not free. They're frozen, right? Just by tweaking their direct orientations, your transport of protons can be done. All right, so protons often are found in acids. Acids are corrosive sometimes, but you can make it not that corrosive. Then around 2017, we thought, okay, well, maybe we should explore ammonium. Ammonia has, protons, not technically 3 protons, but 4 of them. So can we use ammonium? Because ammonium salt, we know they're not so corrosive, right? So, and also ammonium is, not so big. It's like similar size of potassium, right? Now we provided the first device of ammonium-ion batteries out there. And performance-wise, it's more stable. It's more stable than potassium and sodium. That's kind of interesting. So we are moving a tetrahedron ion through the lattice, and that ion does a better job than spherical ions. Why? Right? Why is that? So I got a little cartoon here. You have the ammonium ion inside, and it's going to do the monkey bar walking. See this? Right? Switching from this oxygen to that oxygen. It's monkey bar. You have done monkey bar, right? Yeah. Very good for a house. Very good. I couldn't do that. Yeah. So then why it's faster? Because you have the hydrogen bonding, right? You have hydrogen bonding. Potassium ions cannot have the hydrogen bonding. So when you have the proton switching from one hydrogen bonding to another hydrogen bonding, you minimize the activation energy barrier. I'm probably going too far into chemistry, right? But hopefully that's the fundamental behind that. All right, fast batteries can use protons and ammonium ions. Hopefully I have convinced you with that. But if you want to have higher energy, you probably want to use metals because metals are really energy dense, right? One iron, you can actually put up 3 electrons. One zinc, 2 electrons. Okay, so it's better sometimes to have metal as the anode, as the fuel of the battery, so the battery energy density can be higher. And then, of course, simultaneously, my group is diversifying our reach into different ions. So now, iron, right? Funny enough, Edison battery, invented like 120 some years ago. Edison battery doesn't use iron ion as the charge carrier. The charge carrier is hydroxide. It's a conversion from iron metal to iron hydroxide to magnetite. That's the conversion of Edison battery. So again, we just love low-hanging fruit. Nobody has tried to store iron 2+ in a framework. We won't let go of that. So we tried it and proposed this new device. All right, so then what is the challenge? It looks so good, but what is the challenge? The challenge is water is corrosive. You know that, right? That's probably the reason that a lot of houses are not as expensive as they were when they were new, right? Water created a lot of damages. It's corrosive. So I want to show you this. We have 2 pieces of iron, and we are doing the plating of iron, the reverse plating of iron. See how stormy that is? I want to play this again. That's water reacting with iron, creating hydrogen gas. You won't like your battery creating hydrogen gas, do you? Right? So that's a problem. That's a problem. So what do we do? What do we do? So we became physical chemists, right? So I've been working with my colleague, Professor Chong Fang, a lot by using his femtosecond laser to understand how water behaves. So we tried this electrolyte, concentrated electrolyte. We tried low temperature electrolyte, and we learned something that is really, I love this title. It's really mind-boggling. Strengthening aqueous electrolyte without strengthening water. Okay, so there's some science behind it. I don't have time to explain. And we also studied the basics of ions behavior in water and the impact of water. So we got one conclusion. What water molecules are stable? If you think about it, gaseous water, vapor, the HOMO-LUMO levels, HOMO is highest occupied molecular orbital, LUMO is lowest unoccupied molecular orbital, right? The HOMO-LUMO level is 10 electron volt, 10 electron volt for water vapor. But your water will be electrolyzed into hydrogen gas and oxygen gas with a voltage, in theory, 1.23 volt. This vapor is 10 volt. This liquid is 1.23. Why? Because water stability is weakened by strong neighbors. If you make the neighbors weakly interacting with your water molecules, they will be more stable, right? That's the meshes we have shared with the field. And I want to show you this. This is very interesting. This is aqueous solution, lots of water, right? You have done the experiment. It's for fun. You can throw a piece of lithium. Don't do sodium. It will be a disaster. Lithium is okay if you have a goggle. You do it in a fume hood and with lab coat, right? So a fire retarding lab coat, right? So lithium is fine with that. And that's how stable our new aqueous electrolyte with a piece of lithium. Nothing happens because we just made all the neighbors of water molecules weakly interacting. That is lithium, right? That's lithium. So that's what we did for the aqueous battery field and for the electrolyte. Now, you have turned the spear down a little bit. It's not as sharp as before. Water is weakened. We don't want to actually have water that corrosive. Water is less corrosive now, okay? The next thing is to build an armor on your metal anode, okay? So that's what we did. And we built something called a solid electrolyte interface. Very thin layer, passivating. You know, you can use aluminum foil, right? You can wrap up your sandwich. Cooking with aluminum foil is not recommended in the oven. Covering is fine. Don't use that as the base. Because if you have any acid, it's going to release aluminum ions. And you're going to have that in your body. Don't do that. So I learned that from watching some videos, obviously. Right, so passivation works. And we got a new study. I have to disclose this startup we funded. And it's going to be based on trying to commercialize this technology. All right, so now I'm going to switch the gear again. Anions. Anions. We have talked about cations for the last maybe 40 minutes now. How about anions? Most batteries use cations, right? Really rare for anions to be considered as a charge carrier or the functioning operating ion in the electrolyte. So my student, Ismail, he charged a fully charged electrode. And that's how lucky we were to discover that that compound can store anions. We were supposed to discharge the electrode, but he decided to charge it. And we got capacity, which was in the conventional book impossible. Then when we saw the data, we realized that we had anions inserted in the lattice. Okay? So that's when we started working on this field. That's about 10 years ago. I want to show you when I have anions working, what's going to happen. The cations going this way, anions going this way, electrons are transporting this way. Right? So that resembles accordion. So in one of the review papers, we call this type of batteries accordion batteries. Okay? Now, with this new fun area explored, we studied a lot of anions, nitrate. We inserted nitrate into spanyl manganese oxide. We inserted chloride, right? So it was fun. And then our project landed on metals. So I look at a composition of metal and a metal oxide. Do we have some Gen Chem student? What's the difference between metal and a metal oxide in the composition? The single difference is? Yes. Exactly. Thank you. You have oxygen in it. You have oxygen in it. Oxide has oxygen anion, right? You turned metal into metal anion compound by incorporating anions, right? So corrosion of metals can be a battery reaction. And we know metals have a lot of electrons. We just have to design a battery so that the battery can utilize the incorporation of anions. So we did that for copper. This is for aqueous batteries. But at that point, we had a eureka moment. All right, we probably have now, we are ready to enter the high energy battery field. So now I'm going to switch the gear to power batteries, to the lithium-ion batteries. So we proposed the first thing is to move all the ions in this schematic. We have the ions in the electrolyte, right? Electrolyte is playing a role to store the ions. I don't want an electrolyte to play the role of storing electrons because I want an electrolyte to be lean and narrow and thin and as small in footprint of mass as possible, right? So then what I do? I have to move the ions somewhere if I want to use the anion mechanism. So we moved all the ions to the cathode. We have the cathode now incorporating the host of ions and the host of ions to be incorporated and the source of ions, which is the salt. We got a composite of salt with the host, right? So now it's going to look like this, right? We just moved the whole thing to the left, right? So there's a big hypothesis here. The hypothesis is the solid of salt can dissociate their ions upon the request of the electrochemical reaction. And it turns out that that hypothesis is correct. So we shared the idea with the DOE, we got funding, and we had a lot of fun in the last 3 years. So now, the background of lithium-ion batteries. The problem of lithium-ion batteries is the cathode, if I can claim that. We have silicon, we have lithium, but the cathode, we don't have good options and they are expensive. But the cathode market, look at that. $32 billion, 2024, just the cathode. I'm not talking about a separator, current collector, cage, anode, electrolyte, nothing else, just cathode. Right? So, what is the challenge? We have the Tesla battery, NCA, nickel, cobalt, aluminum, alloy, metal oxides. We have the BMW batteries, it's called NMC, nickel, manganese, cobalt. They have high energy density, but they're expensive, and they have issues. We have the BYD type of battery, lithium iron phosphate. The ceiling of energy is too low. We want to be there. Orange, our color, need to be there. All right? So, the problem of cobalt-containing compounds, that is literally how cobalt is mined, right? By hands in the Democratic Republic of Congo. 70% of cobalt comes from that country. Well, I had a quote from Elon Musk. Nickel is the biggest challenge for high volume, long range batteries. Australia and Canada are doing pretty well. US nickel production is objectively very lame. Indonesia is great, right? Being great has a risk. That's an island of Indonesia before the mining happened. That is after. That is after. So, furthermore, we're going to have nickel and a cobalt shortage. right? 2035 for cobalt, 2045 for nickel. So we implemented our idea. So that's Mingyang's work. We mixed iron with the salt, right? We have to design a proprietary mixture of salt. It's not any salt, right? Lithium salt. And we have the capacity. We have the capacity from iron. So we turned metal iron powder into electro materials. And the performance was good. And I got interviewed by Dave Miller on OPB. Thank you, OPB. So then we got even bolder. So we got a salt, right? So there's a serendipity. We got a salt, and it turns out that our salts are oxidized. Initially, we thought that's a bad thing, but later we feel like, yeah, why not? If we can just turn salts, lithium salt, sodium salt as the active mass of the electrodes, they are precursors to be burned in the conventional chemistry. We don't have to burn them. We can just use them. They're like a couple of dollars per kilogram rather than $80 per kilogram for NMC, right? Why we pursue that route? So we did that, and that worked. That worked. So that's the device we have, and that's the performance, good capacity. We are here. We are here. And I have a new startup established. Wesley is helping with that. He's the CEO. So we have a paper now under consideration of a journal. I have 11 institutions to work with, 32 authors, and we have everybody join to help. So I'm really fortunate and honored to have these collaborators. So what is new there? What is new there? When you have a mixture, when you have a composite, you are creating a lot of heterointerfaces. That is where the magic happens. So we are moving from the conventional pure solid-state chemistry to a composite era of chemistry. So it's difficult to analyze, difficult to characterize, but it's probably worth the trial. And we have the platform chemistry. Now we are expanding to sodium, and that's Zhang's work. The sodium battery cathode performing really well. And the compound we use, the cost is about $8 per kilogram. That's how cheap the material is. And the IP is covered widely across the field in OSU IP. All right. So hopefully I have convinced you that when you name a dimension in a multidimensional space, you won't be lost, right? So, and that's the conclusion I have for today. I want to thank my sponsors, the funding agencies. I want to thank the entire chemistry department and my family, my wife Angela, Kimberly, Olivia, my mom. And last, I want to say chemistry is awesome. Thank you.
We have time to take a few questions. And I think it works if I use this microphone and you use that one. Oh, good. Oh, over there. Oh, you're not. You're not. Okay.
All right, so I've actually asked you a very similar question in the past, but I've refined it, so I'm going to ask it again. I'm more in the biology end of things, so I'm not sure if anything like this would work. But in cells, you have the electron transport chain. That's one of the most efficient means of gaining energy that we know of. So is there any way, and I know hydrogen's kind of a, you don't want to mess with hydrogen, but could we scale that up potentially as a renewable battery source? Or is
for the bio source of protons?
Yes, sir. That's
a great thought. That's actually the materials for Nature science journals. You know, there are actually microbial fuel cells that use bacteria, that use them, the fuel created by bacteria. And do they use protons? I think they do. The ion charge carrier is the proton. Yeah, so in terms of scaling up, it's certainly possible. Yeah, so it's if you design it well, probably we can have the electrode, both electrodes and everything being, bio, right? So that's actually the field I always wished to enter, but never got a chance. Thank you for the question.
Other questions?
So it's really exciting, but with your new technologies, what are the dangers? You hear about Tesla's burning. Can you mitigate that, or is there, do you have problems that kind of density?
Yeah, NCA and NMC, these compounds are using basically nickel oxides as the framework, and nickel oxides shares the band. Nickel and oxygen, they share the bands. The bands are really close. I'm talking about the electron, where electrons are hosted. So it is a challenge to remove electrons from nickel without the possibility of removing that from oxygen. That's an inherent challenge of all nickel-based oxide cathode materials. So the chemistry I just introduced, it's based on lithium oxyanion salt. So you have lithium, you have another element, you have the oxygen coordinating that element. So it's a very strong covalent bond, like say carbonate. Carbon, oxygen, right? Sulfate. Sulfur, oxygen, very strong covalent bond. You can break it. Lithium carbonate can be totally decomposed. It's going to release some CO2. But we actually managed to prevent that from happening. So that's a key part of that invention. So yes, we are safer because we are not going to release oxygen gas. Yeah, oxygen gas, think about it, for lithium-ion batteries, you have oxygen gas releaser, which is metal oxides. And you have a tank of fuel, which is the electrolyte, made of solvent that is flammable. So that's why. So under regular conditions, lithium-ion batteries are very safe. The only problem is sometimes it's under abusing conditions. That's the problem. Yeah. Thank you for the question.
Thank you.
Thank you.
Well, yeah, thank you. I was wondering if this new technology could be applied to pumped electrolyte batteries. I mean, where the energy is stored in the electrolyte as opposed to the anodes or the electrodes.
Yeah, that's that goes back to the dual-ion battery I mentioned and supercapacitors, right? So when you have dual-ion batteries and the supercapacitors, all the ions are stored in the electrolyte. Your electrodes are temporary host after the device is charged. So it is widely used for capacitors. That's the mechanism. What is actually the challenge of that mechanism or that configuration of the device is that the electrolyte, the function is supposed to be conducting ions. When it just conducts ions, you can make it really thin. You can make it atomic thin, if it's not be shorted, right? But once you use it to store ions, it will be bulky. It will be bulky, and it will take space. It will take mass. It will take the weight. And then usually those devices, dual-ion battery-wise, supercapacitors, their energy densities are usually limited. Yeah, that's why the other device is called a rocking chair. The rocking chair device, they store the ions on one electrode. And the electrolyte is made as thin as possible, as long as it's not going to be, punctured by, dendrite or anything, shorts the battery. Yeah. Did that answer your question?
Well, it seems with pumped electrolyte, you've got...
Oh, you mean the flow batteries? You mean the flow batteries? I got you now. I'm so sorry. You mean the flow batteries? And the flow batteries, here's the picture. Now, just imagine that with me. You got two tanks. Like the tank is the size of this room. Another tank of the size of this room, right there. The wall is your device, right? You flow the cathode and anode electrolyte that are redox active. We call them a cathode for the cathode side, anode for the anode side. You flow them through the device, right? From the tanks, you pump them. So they're actually commercialized. There's a company called ESS, Energy Storage Systems, I think near Portland, maybe Woodburn or somewhere. And they have commercialized, and they are probably already public company right now. So it's definitely viable.
But can it work with your chemistry?
Probably not. Probably not. Our battery, the goal for our devices is to be as compact as possible, as light as possible, so we won't actually have the space for tanks. So the last technology we hope to commercialize is purposely designed for vehicles. Yeah, maybe for drones or robotics. So that means they need to be very dispatchable, right? Moving around, right? Shake it, do whatever you want. It's not going to cause problems. Yeah. Thank you.
I think we can take one more question if there is one. All right, why don't we thank David one more time for his terrific lecture.